Welcome back. In today's video, we want to evaluate the following expression given the complex number z. In the previous video, I said that this would be the last. In that previous video, I had said that would be the last video on complex algebra, but I saw these problem and I thought they look pretty interesting. So in today's video, we're going to evaluate them. So let's go ahead and do that. So we keep our z, which is equal to 1.2, a real part of 1.2, imaginary part of 2.4. We then go ahead and evaluate a, and a is the natural log of z, which is equal to the natural log of 1.2 minus j 2.4. Natural log, we can use the natural log properties in the sense if we have multiplication within the natural log, we can then use addition. And by using addition, we could get that to be in the form of the rectangular form. So let me go through that. So basically I'm saying in order to get this form, get our answer in this form, if we apply, and as you can see, we can go straight ahead and apply the properties of natural log here, but I think it'll be a little bit simpler if we transform what's in the parentheses in polar form, then apply the property of the natural log, and then simplify. So that would be, we go ahead, the natural log, and let's write that in polar form. So in polar form, we have the z is equal, the complex number z is equal to the magnitude of z times the complex exponential e to the j theta. So we can take the magnitude, which is equal to the positive square root of x plus y squared. X is our real part, y is the number, the imaginary part, the number or the coefficient of the imaginary part. And the angle theta we calculated from the inverse tangent of y over x. Thus we can write our complex exponential as j times inverse tangent y over x. That's x. So we go ahead and write our magnitude. We end up with a magnitude of 2.68 and a complex exponential of e to the minus, we keep our minus sign, j 63.4 degrees. Now we can apply the natural log property, and we can take the natural log of the magnitude, and then we can add that to the natural log of the complex exponential, j 63.4 degrees. Simplify that, and we can go ahead and simplify that by saying that this would equal to 0.99 minus j 1.11. But before that, before you even get to that, notice that 63.4 is equal to 1.11 radian. So using, you go ahead, use your calculator, plug that in. We see that 63.4 is equal to 1.11 radian. If you use the conversion between radians and degrees, then we can write that. We bring this down, and we can write that as j. But if you think about it, right? So we can use the property, and we can get j times 1.11 to the natural log of e, and we know what this is going to equal out to. So that then simplifies to 0.99 minus, that's -1, a negative j 1.11. So the natural log of z is equal to this guy right there. We then go ahead to b, b, e to the z, so e to the complex number z, we can then go ahead and basically use our exponential exponent properties. So if you let's write that out first. So that would be e to 1.2 minus j 2.4, and this could be said, we can call this as, we can use the multiplication property by saying that we add 1.2 plus a negative j 2.4, and that will give us e to the 1.2 times e to the negative j 2.4. We go ahead, simplify e to the 1.2, we get a coefficient of 3.32. Then we apply Euler's identity in this portion. So e to the j theta is equal to cosine theta plus j sine theta. So if we take cosine 2.4, we end up with, well, let's just write that out. So 2.4 minus j sine 2.4. Put that in your calculator, punch that out. You get a negative 2.45 minus a j 2.24. And that is it for B. For C, we're then taking the natural log, we're taking the natural log of the complex conjugate of the complex number z. So notice we already evaluate the natural log of z. So when we take the complex conjugate of z, so if z is equal to a plus jb, then its conjugate, z to the superscript or an asterisk, is equal to a, change our j, the sign of our j, and that is the complex conjugate. So all we have to do is evaluate that and then change the sign on that. So that is then, c is then 0.99 plus j 1.11. And we go ahead, evaluate d, and d is the exponent z conjugate plus 1, and we know z in this case was 1.2 minus j times 2.4. The conjugate of this will end up with a positive j, so we then write that as equal to, that'd be 1.2 plus j 2.4 plus 1, and we add our 1.2 to 2, that's equal to exponent, or the exponential, 2.2 plus j 2.4. We can go ahead and do what we did with our exponential. So we then write e to the 2.2, use the same property, we're adding, so now we just multiply. So that is e to the j 2.4. We simplify our exponential, e to the 2.2 gives a value of 9.025. Then we apply Euler's identity. We take cosine 2.4 plus j sine 2.4, and we end up with a value of negative 6.65 plus j times 6.10. And that's it for C. I might see if I find any more complex algebra problems that I think will be useful in the phasor domain. are useful in circuit analysis, and especially AC analysis, where we convert over to the phasor domain, and complex number will be essential. So that's it for today's problem. See you in the next video. Bye.